The learning objective of this chapter is that the learner will be aware of the alternate fuel systems for marine diesel engines. In the previous chapter, we have looked at the conventional fuel systems for diesel engines and considered some of the more common variations that have evolved, such as variable injection timing. Now we will have a brief look at some of the other variations that you may come across on the vessels that you sail on. We will not go into detail about these systems, only give an overview. You should study the manufacturer's instruction book for details of the actual systems when you sail with them. Many auxiliary engines are designed to operate on fuels other than clean distillate fuels. Residual fuels are, however, not always suitable, particularly when running on low load due to ignition and combustion quality issues. A number of inline fuel blending systems have been developed which allow diesel engines to operate on a mixture of distillate and residual fuel, while avoiding the storage problems sometimes encountered with fuel mixtures. The temperature controller controls the supply of steam to the heater to maintain a constant temperature independent of the viscosity or blend ratio. The viscosity controller output is used to control the speed of the distillate supply pump to maintain constant viscosity by varying the ratio of the two fuels to be blended. If the viscosity rises, the pump speed is increased to add more distillate, and if it falls, the pump speed is reduced and less distillate is added. Another method of control is to give the blend component ratio a load-dependent preset value, which varies throughout the load range. At any given load, the blend ratio is fixed and the viscosity is maintained at a preset value by varying the temperature of the mixture. The temperature will be low for blends with a high percentage of distillate when the engine operates on low load, and high when it operates on high loads with only a small percentage of distillate in the blend. Inline blending can also be used to control the fuel's sulfur content by mixing high and low sulfur fuels to obtain the desired sulfur content of the blended product. In order to overcome ignition delay problems with fuels that also have poor combustion quality that may result in a low and late peak pressure, some systems are designed with pilot injection. In these systems, a small amount of fuel, the pilot, is injected earlier than normal in the cycle and before the main fuel quantity. This allows the pilot fuel more time to heat up to auto-ignition temperature. Once ignition takes place and a flame is established, the cylinder temperature rises and it is easier to ignite and combust the main fuel charge with minimum ignition delay. Most pilot injection systems use an electronically controlled single fuel injector with two distinct injection periods. Pilot injection is also used for dual fuel diesel engines and is described later in this chapter. Fuel injectors operate at the optimum at a particular load or fuel setting. As the load increases or decreases about the optimum point, then injector performance can fall off. In twin injection systems, one of the injectors operates at full capacity at all engine loads, giving an amount of fuel just less than that required for minimum load running. The fuel quantity passing through the second injector is varied depending on the load on the engine. The fixed fuel quantity is injected into the cylinder by the first injector, followed by the varied quantity from the second injector. The system is sometimes considered as a form of the pilot injection system, as it has two injection periods. However, it operates with normal fuel timing and optimized injector performance from the first injector, rather than early injection of the pilot fuel to improve ignition and combustion. The rapid increase in LNG trade by sea has brought with it an urgency to develop dual fuel systems for diesel engines, which allow the boil-off gas from the cargo to be used as fuel. These systems have now been introduced, and there are an increasing number of dual-fuel diesel engines now in operation. The tightening of environmental regulations has also resulted in the use of dual-fueled engines on some ships which do not carry gas cargoes, as lower NOx, SOx and carbon dioxide emissions result from using gas fuels. The dual-fuel system is electronically controlled with the facility to operate on either gas or fuel oil, either in fixed or operator-controllable ratios. Inputs from the engine for speed, power, combustion quality and the air-fuel ratio are fed to the engine control unit. The output from this unit controls the fueling rate to give optimum conditions, including efficiency and exhaust emissions. Different engines operate in gas mode in different ways. In one system, the combustion process is initiated by injecting a light fuel oil as a pilot fuel, followed by injection of high-pressure gas into the cylinder. In another system, gas is added to the inlet air at low pressure, with the combustion process started by injecting a light fuel oil into the compressed gas-air mixture through a fuel injector. In fuel mode, the fuel system operates as a conventional system with electronic control. The use of fuel emulsions has been reintroduced in some recent engine designs as one method of reducing the NOx level in exhaust emissions. NOx production from a diesel engine is dependent to a large degree on the maximum cycle temperature and the length of time that it is maintained during combustion. By introducing water into the combustion process, the maximum temperatures are reduced, so reducing the amount of NOx produced. This, however, can reduce engine efficiency and lead to an increase in specific fuel consumption. Fuel emulsions can also reduce the effectiveness of cylinder lubrication. One side effect of using emulsions with very poor quality heavy fuel oils is that the water in the emulsion flashes off into steam in the engine cylinder. The rapid increase in volume during this change of state can aid atomization and improve combustion efficiency. We have seen in this chapter that developments in diesel engine fuel systems are usually driven by commercial pressures, the quality of the fuel, and/or by environmental concerns. We have looked briefly at a number of developments, all of which you may come across on vessels that you sail on in the future. You should always use the engine manuals provided on board to get specific details about the systems that you sail with. Try the questions in the following self-test to check your understanding so far.